In this video we are going to solve a graph search based problem. It's called max area of island. So you must have solved a few problems on graph theory, and if we have a grid where we have 0 and 1 to represent water and land. So let's say this color denotes land and this bluish dot denotes water. So island is an area of land which is surrounded by waters, and beyond this grid assume that everything is water. So this blue color, so this yellow color is land, or we can say 1 or 0. So in this case, what are the lands? If you see this part, this is a land, it's surrounded by water from all the sides. Similarly, this is also a land. In terms of graph, we call it connected components. Then you see that this is a land, but these two are not connected. This is the difference here. So there are multiple ways to distinguish neighbors. There is a notion of 8 connectivity where we have 1, 2, 3, 4, 5, 6, 7, 8 neighbors. So even diagonal 4 neighbors are considered, but sometimes we are just considering 4 neighbors, that is top, bottom, left and right. So in this case we will use 4 connectivity to determine the neighbors. So this small piece of land is not connected to the second one, and we have to find all those lands and we have to return the area of the largest land. So in this case, this area is 1, this lower bottom is also 1, area of this one is 3, and the area of the fourth one is also 3. So we have to return 3 here, one of these, whichever is maximum. So how we will solve it? So you can identify it's a graph based problem, and we can do it using depth first search. So we will have to run a multiple depth first search for this graph, since there are more than one connected components. So more than one connected component can be there. So multiple DFSs will run and terminate. So each DFS will denote one DFS on one land, because from DFS you can only reach vertices which are reachable from there, that is connected. And we will keep on doing DFS until we visit all the nodes, that is we have visited the complete island. Then we go to next island, again do DFS, we visit all the area in this land and keep track of the maximum. So what we will do, we will start 2 loops. Let's say this I value is iterating through this rows and j iterates through this columns, and this length is m, or let's call it c, and this is number of rows is r. So for I equal to 0 to r minus 1, and for j equal to 0 to c minus 1, if let's call it grid ij is equal to 1, then we start a DFS. There is no point in starting a DFS from water, we will not visit anywhere. So if it's 1, that is its land, we trigger a DFS from here. At this ijth position we trigger a DFS, and we, in all the graph traversals, we keep track of a visited array or grid. We will keep it of the same size, r and c, and whenever we visit any land we mark it as visited. So what will happen? It will first trigger DFS here. So this is 0, this is 1, indices starts from 0. So first we will trigger DFS from 0, 1, and within DFS what we will do, we will look at all the 4 sides. If we have any land which is not visited, and we will use this visited grid to keep track of which node we have already visited. So this is very important. Why? Because let's say we have just 2 cells, and these are land and there are water elsewhere. So from here we see that we have a neighbor which we have to visit. So we come here, and again here we will find this is 1, or A, this is B. So from A we go to B because B is a neighbor, and from B we will again go to A because A is a neighbor, and so on. We will keep repeating. So that's why we have to keep track of visited. Now once we start DFS from this small 0, 1, we will look at all the neighbors. Left side no neighbor, bottom no, top no, right no. So we are done with DFS. This DFS will terminate and it will return 1. So it found a land of area 1. So it visited one node in this DFS. Then this loop will continue. We will come here, I is still 0. We will come here, not land, not land, not land. Then I becomes 1 here, and J is again 0. This loop, not a land, not a land. Again we found a land and we see it's not visited. So we start DFS from here. So when we come at some land, we mark it as visited. So let's say this red denotes visited. So we came here, we started a DFS. So this next DFS will be DFS, this is 1 and this is 2. So we mark it as visited. Within this count is 1. Left neighbor nothing, top nothing, right nothing, bottom yes there is a neighbor, not visited. So we start a DFS again from here. So 1 plus DFS of this value, which is 2, 2. Again top there is a neighbor but visited, left nothing, bottom nothing, right neighbor which is unvisited. So it will call DFS of this value 2, 3. This value. Again this is visited, and now there is no more neighbor. So it returns. So this 1, 2 will return 3. It visited 3 nodes. And now this loop will continue. So we were here where we triggered DFS. We come here, not a land, not a land, not a land. Again it's a land but visited. So we continue. Again a land but visited. Next we come to this point 3, 0. So we trigger DFS 3, 0. And the same way this will be visited, then this and this. This will again return 3. So whatever we are keeping track of result, maximum value, it will remain 3. And then we will continue. We will come here, not a land, not a land, not land. Land but already visited, visited, not a land and unvisited. So we trigger DFS at this last node and this will return. So we trigger land DFS at 4, 3 and it will return 1. So which is not better than 3. So finally we will return 3. So what is the time complexity? If you see, we iterated through this complete grid. So R cross C. And what else? Did we visit any node multiple times? Yes, sometime, like we already visited this node which I am highlighting in yellow when we trigger DFS from the node above it, and next time again in this loop grid we visited it, but it will not be visited many times. It will be just visited from its neighbors and not more than that. There can be maximum 4 neighbors. So still the time complexity remains R cross C. Number of rows, number of columns, so number of cells in the grid or number of nodes in the graph. And space complexity, we keep track of visited for each node. So space and time, so time is O of R cross C, space is also O of R cross C. So for a space we can use the same grid input that is given to us. In that case we will not need that. So how we will do it? So we have some zeros and some ones. Okay, so only ones. So zeros we can leave it as it is. We will never go to 0 in any way. Similarly we will never go to visited nodes. So we don't need to change zeros. Only ones. When we visit a node 1 as a part of DFS, we will mark it as, we will make it 2. And while DFS we will always go to a node whose value is 1. So we will never visit 2 again. Again make it 2. Let's say here again it was 1. We will make it 2, and when we have are ready with the result, so result is ready. Now no longer we need this value, we can revert it back. So traverse once again through this grid, whatever was 2 make it 1 and get back the grid, or you can leave it if it's not required. That will depend on the use case. So you can save space there at the cost of modifying the grid, and then if you want it back you can modify it again in R cross C time. So let's write the code for this in C++ and Python. So what we will do, we can modify the input grid itself, but it's up to you. So this is the problem, and you can go through this example. In this case, this output is 6 because these two are not connected. So the one in the darker orange is the island we are talking about. First we will write in C++. So we need to define a function, recursive function for DFS, and we will pass the same grid and make sure to pass it by reference and the current cell where we want to run the DFS. So number of rows is grid dot size, and it's given that there will be at least 1, so you can ignore the empty case, and number of columns is grid 0 dot size. So in general case you have to check that this R is more than 0, then only you can do grid 0, otherwise it will crash your program. But in this case we are not worried about that. Now if I is less than 0, so we are listing the invalid cases, or j is less than 0, so these are invalid cell indices, or I is equal to R. Let's write I greater than equal to R, but we will never reach greater than because we are incrementing it one by one. So but let's write it greater than equal to R and j greater than equal to C, or grid I j is not equal to 1. So these are the cases when we will not trigger a new DFS. We will trigger a DFS when the indices are valid and the grid value is 1. Then only we will trigger DFS. In other cases return 0. Then we will make it so when it goes past this line, that means everything is fine and we have a neighbor. We have a grid cell which is a land and not visited. So we mark it as 2 visited and return 1 for this current cell and DFS on all the neighbors. Grid. So 4 neighbors are I plus 1 j plus DFS grid I minus 1 j. So I plus 1 means bottom neighbor, I minus 1 means top neighbor. Then I j plus 1, that means right neighbor, similarly left neighbor. And this function is done. Now the main function, again we will need R and C for that running the outer loop, for triggering multiple DFSs, and the result is initialized to 0 for int I equal to 0, I less than R plus plus I In fact, this check is not required. I am just adding it so that we don't trigger a DFS from all the cells in this. So it's better to check for one beforehand. Result equal to max of earlier result, or so here you can before returning, you can make this grid back to what it was. Since we are changing the grid, we are making 1s to 2. That I leave up to you as an exercise. Now let's see if it works or not. So there is some compilation issue. Okay, so it shows here. Okay, so we have not closed this bracket. And the solution matches. Let's submit. And the solution is accepted. Now we will do the same exercise in Python. And the Python solution is also accepted. So what we did here, we brought this RNC outside so that it can be used by this main function as well as this DFS, or we can skip this line also. So let's check. So it's working even without this, so we don't need, since we have made it global to this function. These RNC do not change. And let's submit again. And it's working. So the same logic, just slight change in the code. So thanks for watching. See you in the next video.